In our previous video, we have seen the underlying concepts involved in the balancing of several revolving masses in the same plane. In this video, we shall solve a numerical problem on the same topic, which can be solved by both analytical and graphical methods. So let's get started. Hello everyone, welcome to my channel. It's me, Dr. V. Jayakumar. I make lecture videos for the benefit of mechanical engineering students. Before we proceed, please press the subscribe button and also the notification bell icon so that you will get notified every time when I post a brand new video on this channel. As always, before jumping into the problem, we will recap the prerequisite concepts required to solve this problem. There you are. This is the flowchart explaining the various categories of balancing problems that we will be studying. In this, we are going to solve a problem on balancing of several masses rotating in the same plane. So this is the given problem. So several masses rotating on the same plane will be given. Our aim is to determine the balancing mass value as well as the position of the balancing mass mb and theta p. This problem can be attacked by two methods, namely analytical method and graphical method. We have presented in detail about the various steps involved in the analytical method. The summary is given here, which we'll be using while solving our problem in a while. Same way, the various steps involved in this graphical approach of solving that same problem is also given. You could refer to our previous video for the detailed understanding of the concept. So these are the various steps that we are going to apply while solving a numerical problem. Okay. So now, are you ready to solve a numerical problem? Let us understand the problem clearly. A rigid rotor has all its unbalance in one plane and can be considered to consist of three masses. So we have three revolving masses revolving in the same plane. That's what that statement says to us. The values of M1, M2 and M3 are given. Mass 1 5 kg, mass 2 is 3 kg, located at an angle 165 degree counterclockwise from mass 1. So from the location of the mass 1, mass 2 is located 165 degree measured counterclockwise. So the given mass as well as location of the mass 2. Same way, mass 3 value and its angular position also given, which is nothing but mass 3 equal to 8 kg at an angle 85 degree clockwise from M1. Also we have with us the radii of rotation of three rotors, R1 equal to 20 centimeter, R2 equal to 8 centimeter, R3 is equal to 14 centimeter. So what we are supposed to determine? When these three rotors rotate, we need to check whether the system is in balance. If the system is not in balance, we need to balance it by adding a balancing mass. That's what exactly they are asking us to determine. So the given radius of rotation of the balancing mass as 10 centimeter, right? So we need to determine magnitude and location of the balancing mass to be added to this three rotor system so that it will be in complete balance. Is that problem clear? Yes. As always, let us list out the given data. So they're given as M1, M2, M3. Then all three radii of rotation of those three rotors are given as 20 centimeter, 8 centimeter, 14 centimeter respectively. And also they are given radius of rotation of the balancing mass, which is nothing but 10 centimeter. Just I'm listing down all the given data from that problem. So as discussed, we need to determine magnitude of the balancing mass MB and also its location, angular position theta B. Okay, you know that this problem can be attacked by two methods, one by analytical method, another one by graphical method. Unless otherwise specifically asked in your university question papers, you can solve by any one of those. However, for our understanding, I am going to solve this problem by both the methods. First, let us solve the problem by analytical method. So we know that m omega square r is the centrifugal force, which is the unbalanced force. Since all rotors are rotating with the same angular velocity omega, eventually we are going to balance the resultant unbalanced force with the balanced force. The omega square value will get cancelled out, and hence mass moment or m into r should be sufficient. So we can find centrifugal force of each mass now, or in other words, we can find mass moments for all the three masses. We know all the data record for this. So just by mere substitution, we'll be getting the record values. So we are done with step number 1. We found centrifugal forces of all three masses. The step number 2, we will resolve the centrifugal forces horizontally and vertically, and we will determine summation of all horizontal components sigma fh and summation of all vertical force components summation of fb. That is your step number 2. Here the position of mass 1 is not specified, whereas position of mass 2 and mass 3 with respect to mass 1 are given. So what can I do? For my simplicity, let me consider as if mass 1 is acting horizontally here. So theta 1 is equal to 0 degree. Okay. So it is given that mass 2 is acting 165 degree from mass 1 measured in counterclockwise direction. So what is that angle? This angle is theta 2, 165 degree. Same way, the third mass is given as 85 degree measured from theta 1 in clockwise. For consistency, I am taking angles the same direction. In this case, in the clockwise direction, 275 degree is the theta 3. This analytical method is nothing but determination of resultant force and equilibrium force that you all might have studied in your engineering mechanics subject. That's what we are doing now. Okay, so now I can easily determine sigma fh. Right. So I know all the force values, three force values and their angles. So mere substitution, I will be getting sigma fh and sigma fv. So we got two components, sigma fh and sigma fv. Now I think we can determine the resultant force. Resultant force is nothing but resultant out of balance or unbalanced force. That's what step number 3. How can I find resultant force value? We know that substituting the obtained value in the previous step, we can very well determine the resultant unbalanced force R. So by simplification, we get resultant force value as 1.363 kg meter. We also know how to find the angle of that resultant force. We know that minus 50.62 degree denotes that the resultant force acts at 50.62 degree measured in clockwise direction. So we have completed step number 3. Okay, right. Now we have come to last two steps, determination of magnitude of balancing mass and also its direction. Okay, what we understand from the resultant force, when we have resultant force, it means that we have some unbalanced out of balance force in the system which is not desirable, which needs to be eliminated. How? By adding externally some balancing force so that we do not have any out of balance force. That is the idea. How can we balance this system? By introducing a balancing mass exactly in the opposite direction, that of the resultant force, as shown here in the dashed line. So step number 4, to find MB. We know that centrifugal force created due to the balancing mass must be equal to the resultant force, or in other words, MB or B must be equal to the resultant force obtained. So MB we need to determine, RB it is given in our problem, zero point 0.1 meter, or just now we found. From this we can find the value of MB. So that means 13.63 kilogram of the balancing mass needs to be introduced here. What is the radius of rotation of the balancing mass? 0.1 meter, which is given in the problem, right? So that is step number 4. Now we can complete step number 5 easily, which is nothing but to find the location of the balancing mass. We know that the location will be exactly opposite to that of the resultant force, or in other words, angle of the resultant force, either I can add plus 180 degree or I can add minus 180 degree. What it means, either I can measure from here or I can measure from here. That's what it says, plus or minus 180 degree. There we are. So we have obtained the answer MB and theta B. So this is my answer, theta B 129.38 degree and MB as 13.63 kg. That means we have already 3 rotors. Now I am going to add 4th rotor. What is the mass? 13.63 kg. Where I am going to add it? At 129.38 degree from M1, measured in counterclockwise direction, having the radius of rotation is equal to 0.1 meter. Now I have 4 revolving masses in the same plane. Now if I switch on the motor, now if all the 4 rotors rotate, you can see that the system is in complete balance. Now there are no unbalanced forces. There will be no vibration. It is completely balanced. That is the meaning, or that is the interpretation of these numbers. Is that clear? Yes. Let us try to attack the same problem by graphical method. Step number 1 says we have to draw the space diagram, configuration diagram. Since all rotors are rotating the same plane, if I see from the front view, I will not be getting any clue about the angles between those rotors. From the front view or top view will not give us any clue about where the rotors are, oriented. So what I will do, I will see from the side view of those rotors. When I see from the side view like this, I can know, right, mass 1 is, located here, 2, 3, like that. So what I'm going to do, I am going to draw the side view or angular position of the given 3 masses. Here, the angle needs to be drawn to the scale, exact scale. This is the position of first mass. I assume first mass is acting horizontally, theta 1 equal to 0 degree. 165 degree. So this is the direction at which M2 acts. This is mass M1. They're given mass 3 is acting at an angle of 85 degree measured clockwise. Angular position of planes of masses. This is what I call space diagram. Is that clear? Yes. Now let us go to step number 2 to find magnitude of centrifugal force of each mass. We know how to find centrifugal force. Right. So we got the FC1, FC2, FC3 values. Now let us go to the very important step known as force polygon. So we know the magnitudes and we know the directions. It is easy to draw force polygon by using the concept polygon law of forces. Let me choose a scale for constructing a force polygon. So anywhere, let me start my first point. So this is horizontal. I can take the 4 centimeter line to my scale. This is my starting point O. So this is mass 1. So I can call it as O1. So we are done with force 1. Shall we do with the force 2? Remember, it's a vector addition. I am going to draw parallel line to this. How to draw parallel line? I suggest you to use the roller scale. Once you can have the scale there, then you can roll it out. So here, I am just bringing it here. So from 1, I am going to draw a line what is that value? 0.24, approximately equal to 1 centimeter line. So what is the third one? Third one, I am going to draw parallel to this, right? So from this line, I am going to parallel. From where? Vector addition. So we will start from the tail of the previous vector. So from here, I will be starting. So what is the magnitude? 1.12. So 1.12 divided by 0.25, you would be getting about 4.5 centimeter. Am I right? What is the direction? So radially outwards. So I will be drawing this 4.5. Yes. This is my closing point 3. So how many masses we have? 3 masses. How many forces? 3 forces. We got 3 vectors. 1, 2, 3. Where we have started? At 0. Where we have ended? At 0.3. Is this force polygon closed? No, not closed. When force polygon is not closed, what it means? It means that we have some unbalanced, out of balance force. So what is the magnitude of out of balance force? That magnitude will be equal to the closing side of the polygon. I'm going to join the first and last point here. What is that? That is the closing side of the polygon. This closing side will give us the value of resultant unbalanced force. By measuring this vector O3 and multiplying by the scale, you will get the answer. So I will be measuring this. So that multiplied by the scale, I am getting the answer as 1.4 kg meter. We know that resultant force is equal to mb or b. So resultant force is given 1.4, mb we need to determine, rb is given. So from this, mb is equal to 14 kg is the answer. Now last step, step 5, to find position of the balancing mass theta b. Let me draw a line parallel to FCR to this main diagram. This diagram shows the direction of resultant force. The balancing mass has to be applied in the opposite direction. So this is the direction at which balancing mass will be located. I should be measuring now this angle. Measuring that angle, I will get the required answer theta b. So I am getting the answer as about 130 degree. There you are. So we have got the values of mb and theta b. That's it. We have determined the balancing mass and its location by graphical method. You can very well compare these two answers with that of the analytical method. You can find both are almost similar or the same. The error may be due to some graphical construction method. Okay, I have given here a problem for practice which you can try at your home and check the answer given. Hope you found this video useful. If so, like this video, share it to your friends and subscribe the channel. That's it. Thanks for watching. Take care. Bye.